So in this video, we're going to talk about DC current. Before we do that, we have to define what current is in general. So in physics, current is nothing more than the flow of charged particles through some sort of conductive medium. So within engineering or electrical and computer engineering, the most type of conductive medium that you will see will be metal. And if you remember back to your chemistry class, whether it was in college or in high school, you remember that the actual structure of the individual atoms within a metal, the electrons typically are very far away from the nucleus. Remember that inside the nucleus is where you have those positive charged protons. So their attraction is less because they're actually farther away from the actual nucleus. And they don't have a lot of friends around them in those outer shells. That's the idea of a valence electron. If you don't know any of those terms, it's totally okay. Just know from a chemistry point of view that metals tend to have electrons that aren't in their kind of complete groups that are very far away from the nucleus. And those are the actual electrons that actually move when a voltage is applied to that metal. So you can have a conductive medium, which is actually a metal. And you can see those within a circuit. Maybe they look like these actual small jumper wires and electronics that are used to connect things to one another. If you've seen a printed circuit board or a PCB, those little traces of copper that interconnect components, that's a metallic conductive medium. However, they don't necessarily have to be metal, and they don't have to be negative charges that are moving through them. In semiconductors, you can actually have the flow of either positive or negative charges in that actual doped semiconductor lattice. And if that makes no sense, that's totally okay. Just note that in a semiconductor, you can have positive or p-type conductive materials, or you can have n-type or negative conducting materials. If you're familiar with battery technology, maybe you've heard the term lithium-ion battery. Well, lithium-ion is actually a cation, right? It's an actual atom that has been made to have a net charge, and it is a net positive charge. So in that case, it's going to be positive charges that are actually moving as conductors in that medium. So the key point that I want you to realize there is it's not just one particle type. It's not always electrons that are actually moving in a DC current or in any type of current for that matter. It can be positive charge carriers that are moving as well. Current is nothing more than the flow of charged particles through some conductive medium. However, what we're going to do in order to kind of have a consistent actual way of modeling is whenever we're analyzing the simple circuits that we're going to be doing in this class, we're always going to assume that the charged particles that are actually moving are positive. And what that's going to allow us to do is to have a sense of intuition that the charges are always going to move from high potential to low potential. So if I have an actual DC source that's connected across some sort of conductive medium, we have an ideal that the actual current will move from high potential to low potential. And remember that direction of flow will always be the same because it's a direct current circuit. And that ideal of always assuming that the charge carriers themselves are positive is what's known as conventional current theory. So it sounds like a fancy term, but all that it means is we're going to assume that in the circuit we're analyzing, the charge carriers themselves are positive. And what that means is that if we have a conductive medium in the real world, so in our model, we're always going to assume that it's positive charge moving. So if our model is actually describing something where the interconnections are metallic, the actual way that electrons are moving is going to be the opposite. So that's a trick question that often shows up in your intro to DC circuit analysis or physics courses. Just know that in the modeling, when we're actually modeling DC circuits, we're talking about the movement of positive charge. So if it turns out that what we're modeling actually has electrons moving, the electrons are really going the other way. So what else can we say about DC current? Well, you actually produce DC current through the application of DC voltage. That's probably not surprising to you. So if you have a DC voltage whose polarity is always staying the same over time, this node is always that much higher than that node, that means it's going to push or drive a DC current through the actual load. So that direction will stay the same over time. How do we model it? Well, within an equation, we're actually going to represent current by the symbol I. And that's a little bit confusing to people. They might say, well, why not C? It turns out C is already the unit for, already the abbreviation for the SI unit of charge or coulombs. So electrical engineers just tend to use I to abbreviate current. Current is measured in the SI unit of amperes. It's kind of abbreviated by an A, and oftentimes it's just said more shortly in terms of amps rather than amperes. And if you talk about one ampere of current is, so if I were to have a charge carrier and say it's like this wide, this is a cross section of it, and I were to count all the coulombs of charge that were coming through that cross section in a second, if there was 1 coulomb of charge, which a coulomb is just this huge bundle of fundamental charge units. If you notice here, it's on the order of 10 to the 18th electrons. If that much charge were coming through that cross section in a second, I'd say that that circuit had 1 amp or 1 ampere of current. So what you notice here is that if when you talk about most electronic applications, so maybe you've been outside or you've had a breaker break in your house or actually trip, and you go out to your breaker box and you look at the writing on there and you see something like 15 amps. Well, obviously that's AC, but still that unit of current is the same, 15 amps. So on household applications, an ampere is a pretty good unit of current. However, if you're talking about electronics, what's going on inside your phone or inside your laptop, an ampere of current is way too big for most non-fault situations. You're going to be dealing with currents that are much smaller. So what we're going to use is metric prefixes in order to scale them down. We might use a milli, which means 1 over 1,000, or we might use micro, which means 1 over a million. But just note that even though the SI unit of current is amperes, oftentimes you see it adjusted or scaled with those metric prefixes. One other thing I want to say is when you talk about currents and you draw them in a circuit, we're going to use arrows. And arrows are going to be a really nice thing because we're not going to actually vary the length like we did with vectors in order to denote how big the current is. However, we are going to put the head of the arrow in such a manner that you can see the direction that current is actually flowing through the circuit. So that's why arrows are a good choice for denoting current in a circuit. So if I have, remember I'm doing conventional current theory as we talked about. So when we draw an actual circuit, if we have a direction of current flow and it turns out that that's positive, that is conventional current or assumed to be positive charge carriers. So if it were to be that we're modeling the flow of electrons, electrons are actually going the other way. You can, and it's very rare, have an ideal current source. For those of you that are going to take an actual circuits class, you will deal with analyzing circuits that are excited by this type of ideal current source. You see the schematic here on the right. It's just an arrow with a specified value on the left. And all that these do is they push a certain amount of current through a load regardless of what the load is. So if you think about it, if the load is very big, we haven't talked about Ohm's law yet, but remember when you're working with circuit quantities, always think of voltage as push and current as flow. So if you're trying to push an amount of current through a load that is very tough to push current through, you're going to need a lot of push in that case. So these ideal voltage sources, basically they can develop enough potential across their actual nodes to drive that current through whatever load you connect. And that's why they're ideal in this case. So you can't, these are just a valuable modeling tool for those that are going down the EC road. When you work with actually transistors, you'll see that you can equivalently model them using these ideal current sources. In addition, you can actually can configure benchtop power supplies. For those of you that are maybe taking a physics class where you're dealing with some electrical instruments, you can configure them to behave like ideal current sources to some extent. So just know that those they exist from a modeling point of view, and you might see them down the road. But the main thing that I want you to get out of this kind of subset of lecture, and I'm going to ask you on the homework, is make sure that you know the SI unit for current, that you know the symbol that's used in an equation, and so on. Much similar questions that I asked you for the DC voltage source content.